Attention! A mysterious object from beyond the solar system is heading straight for the Sun. What secrets does this interstellar visitor hold? Here's what we know so far. In 2025, astronomers made a discovery that would change our view of the cosmos. It wasn't a common asteroid, nor an ordinary comet. It was 3I Atlas, the third interstellar object ever detected by humanity. Its name, 3I for being the third interstellar, and Atlas for the system that discovered it, reminds us that we are just beginning to understand what hides in the vastness of space, but what makes 3I Atlas truly exceptional isn't just its extrasolar origin. It's the precise moment it has arrived. Right now, the Sun is experiencing one of its most intense cycles, the solar maximum. Every 11 years, our star enters a state of uncontrolled fury. Solar storms, coronal mass ejections, and extreme radiation fill nearby space. It is the worst possible time for an interstellar visitor, or perhaps the most revealing one. And 3I Atlas is heading directly into the heart of this solar storm. It follows a hyperbolic trajectory, not circular like the planets, but like an arrow that barely grazes its target before continuing its eternal journey. On this path, it is being exposed to levels of radiation it hasn't experienced in billions of years. Here comes the most intriguing part. This object does not show normal behaviors. If it were a common comet, we would expect a tale of gas and dust, sublimation, predictable activity. But with 3I Atlas, there simply isn't enough data to confirm anything. The mystery deepens because during its point of closest approach to the Sun, the perihelion predicted for October 29, 2025, the object is in solar conjunction. That is, it is right behind the Sun as seen from Earth, becoming invisible to our telescopes. We are literally blind to what is happening. NASA has not provided recent images. The European Space Agency only published a limited set. Other space agencies remain silent. Meanwhile, 3I Atlas is being bathed in cosmic fire, and we cannot see it. But there's something even more terrifying. 3I Atlas is not only approaching the Sun, it is also aligning with an extremely active region of sunspots. Areas capable of generating Class X energy storms, the most powerful that exist. This perfect alignment is about to occur. Imagine this scene. The solar surface is dotted with active sunspots designated AR3462 and AR3468. They have grown rapidly, generating frequent M-class bursts and occasionally reaching X-class. These explosions release high-frequency electromagnetic radiation, X-rays, and extreme ultraviolet that propagate at the speed of light. They instantly impact any object in their path, and that path points directly at Atlas. Why is this crucial? Because solar radiation isn't just light. It exerts physical pressure that can affect objects with porous or unstable structures. Volatile materials on the surface of 3I Atlas, if it has any, could begin to sublimate violently, ejecting gases and dust that detectably alter its trajectory. Even more intriguing is the interaction with the plasma of the solar wind. This constant flow of charged particles, combined with varying magnetic fields, could activate electrical phenomena in the object's coma, if it possesses one. In traditional comets, these effects generate ionic tails, fragmentations, and even complete disintegration. But here's the problem. No one has confirmed the existence of a coma around 3I Atlas. This adds another layer of mystery. Is it really an interstellar comet like Borisov? Or is it something denser, more compact, more resilient? As the object moves at over 65 kilometers per second, it does so in complete darkness for our instruments. It traverses a region where the Sun acts as a shield. We cannot look because the Sun is between us and it. Orbital calculations reveal something surprising. In a few days, the most active sunspots will be perfectly aligned with 3I Atlas's position. This coincidence is not common. When energy and matter meet under extreme conditions, something always changes. Everything that enters the solar system transforms. Not by accident, but by fundamental laws of the universe. No one escapes gravity. No one survives this light intensity without consequences. When we talk about solar radiation, we don't just mean visible light. It's a full spectrum that includes ultraviolet, infrared, radio waves, energetic particles, and, in extreme cases, X-rays. This type of energy doesn't just illuminate, it erodes, transforms, disintegrates. Traditional comets, when approaching the Sun, transform radically. A dark nucleus becomes a body surrounded by a bright coma, with tails extending millions of kilometers. This phenomenon has been documented for centuries. But with 3I Atlas, the story is different. The few data obtained before it disappeared behind the Sun indicate that it did not show a particularly active coma. Some telescopes captured a faint envelope, but nothing comparable to what was expected for a comet at perihelion. Does this mean it lacks volatile materials? Or is its composition so different from our comets that its behavior escapes all known norms? Recent studies suggest that sudden exposure to intense solar radiation can induce internal fractures in interstellar objects. The reason is simple. These bodies have spent millions of years in the absolute cold of deep space. Suddenly, they are heated to hundreds of degrees in a matter of days. This uneven thermal expansion generates cracks, internal explosions, or complete fragmentation. We saw this in 2020 with comet C 2019 Y4 Atlas, not Interstellar, which collapsed unexpectedly as it approached the Sun. It demonstrated that even large objects can yield to sudden thermal pressure. The case of 3I Atlas is more delicate due to its hyperbolic trajectory. If it fragments or disintegrates, any subtle change in its mass would alter its future trajectory. Its exit from the solar system might not be as predicted. Even a small deviation would be enough to be trapped by the gravity of some planet, or the Sun itself. And there's another invisible factor at play: the solar wind. It's not wind in the terrestrial sense. It's a stream of charged particles, mainly protons and electrons, that continuously escape from the Sun at speeds between 300 and 800 kilometers per second. Although they have minuscule mass, when they accumulate, they exert constant pressure on everything they encounter. The solar wind is responsible for auroras, satellite communication disruptions, and, in extreme cases, failures in terrestrial power grids. But outside our planet, its effects are more radical. For comets, the solar wind interacts with ionized gases in the coma, forming ionic tails that always point away from the Sun. It can also induce electrical charges on surfaces, generating complex reactions we don't yet fully understand. In 3I Atlas, this interaction is especially interesting due to its speed and angle. It follows a hyperbolic trajectory. It doesn't visit the Sun as an acquaintance. It crosses it like a stranger in hostile territory. This movement creates an acute angle relative to the solar wind flow, which could generate a plasma-induced shock wave, similar to the bow of a ship parting water. If this wave forms around 3I Atlas, it would be observable by space probes. If it doesn't form, that's also a signal. It means its interaction is different, possibly due to its density, structure, or composition. This is where scientists focus their attention, because these variations can reveal much about its origin and history. Did it form near another star? Was it previously exposed to hostile environments? The answers could be on the way. But there's a greater complication: the solar magnetic field. The solar wind travels accompanied by a complex and determining structure: the Sun's magnetic field. This field is not static, it's dynamic, chaotic, changing. It extends far from the Sun, forming the heliosphere, a gigantic bubble that envelops the entire solar system. When an object like 3I Atlas enters the heliosphere, it introduces itself into an invisible labyrinth of magnetic field lines. These lines bend, twist, and reconnect, generating unpredictable energy events. Sometimes, two opposing lines come into contact, break, and reconnect, releasing enormous amounts of energy, a phenomenon called magnetic reconnection. Why does this matter for 3I Atlas? Because objects traveling through this field can acquire an electrical charge, especially if they possess a coma or interactive surface. Such a charge can provoke torques that alter its rotation, non-gravitational accelerations, and even sudden fragmentations if the internal pressure exceeds the structural cohesion. This type of event has been observed with comets in the past. Asteroids like Bennu and Ryugu showed unexpected changes in their rotation, possibly due to similar electromagnetic phenomena. But with 3I Atlas, the scenario is more extreme, because as far as we know, it had never been so close to a star in its entire existence. Right now, its trajectory takes it through regions of the solar magnetic field associated with recent coronal mass ejections. If one of those ejections crosses its path, the object will not only be hit by particles, but by an expanding magnetic structure that could amplify effects on its rotation or integrity. In essence, 3I Atlas finds itself in the middle of an invisible but tension-filled storm. A storm that emits no light, but can tear away matter, distort trajectories, or unleash unexpected changes. And if those changes occur, perhaps we can detect them not with images, but with something more precise: subtle variations in its orbit, measured by radar and mathematical modeling. But if those measurements reveal a deviation, the story could take a completely different turn. From its initial detection, 3I Atlas has been classified as a hyperbolic trajectory object. It is not in a closed orbit. In other words, it will not return. It entered the solar system from interstellar space, and if nothing strange happens, it will leave forever. Astronomers calculated its trajectory precisely enough to ensure its passage would be brief. But now that it is in the most energetic zone of the solar system, new questions arise. Could its orbit change? And what would that mean? In celestial mechanics, an object only changes its trajectory significantly if it receives a powerful external force, like a collision, asymmetric material ejection, or massive gravitational influence. But in 3I Atlas, radiation pressure and interactions with the solar wind and magnetic field could provoke non-gravitational acceleration. This phenomenon was observed before with Oumuamua, the first discovered interstellar object, which showed a slight but constant acceleration not explained by gravity alone, without clear signs of a cometary tail. At the time, theories like sublimation of molecular hydrogen or expulsion of invisible gas were proposed. With 3I Atlas, the logic is similar. If something pushes it, even minimally, it can alter its future trajectory. With the extreme levels of solar radiation and wind it is exposed to, this possibility cannot be dismissed. An orbital deviation, even by fractions of a degree, would mean that current predictions are no longer valid. It could even generate a tighter trajectory, making the object spend more time in the solar system or, in unlikely but theoretically possible scenarios, become trapped in a highly eccentric solar orbit. For now, orbital simulations are updated with the few available data. The scientific community is attentive. If, in the coming weeks when the object becomes visible again, it doesn't appear where expected, it will be an unequivocal sign that something changed. And then, the inevitable question will be, what deviated it? But even before knowing, astronomers are exploring another silent clue: the real size of 3I Atlas. Because what it seems to be might not be. Determining the size of an object in deep space is not simple. There are no high-resolution images. It also hasn't been possible to observe it continuously from multiple angles. Its proximity to the Sun during its perihelion has further complicated measurements. A primary tool for estimating the sizes of distant bodies is the absolute magnitude. How much light an object reflects at a standard distance. But this method depends on another uncertain factor: the albedo, or the amount of light its surface reflects. An object with high albedo can be small but bright, while one with low albedo can be large but faint. In 3I Atlas, current calculations suggest a size range between 5 and 50 kilometers in diameter. That's an abysmal difference. If it is confirmed to be over 30 kilometers, we would be facing one of the largest objects ever observed transiting through the inner solar system. If it is near the lower limit, it would be more discrete but equally exceptional due to its origin and speed. Size directly affects how it interacts with the solar environment. A larger object intercepts more radiation and solar wind, generating a more prominent coma and tail in case of sublimation. It also has greater inertia, making effects of non-gravitational accelerations more subtle. There is a hypothesis suggesting that if 3I Atlas is particularly large and dense, it could have maintained its internal composition intact since its formation, possibly around another star hundreds of millions of years ago. In that case, it would be a pure relic of the early stages of a planetary system alien to ours, an interstellar fossil. Without visual data or more precise radar measurements, all this remains in the realm of inference. The passage through perihelion could offer additional clues. If upon reappearing changes in its brightness are observed, a sudden increase could indicate cometary activity, helping to infer its active surface and size. A drop in magnitude could suggest it has lost mass or even fragmented. Everything is on hold. Ground-based and orbital telescopes await the moment when 3I Atlas moves out of the solar glare and is back within reach of our lenses. When it reappears, what we see or don't see could rewrite everything we think we know about it. The true importance of 3I Atlas doesn't lie solely in its size, speed, or trajectory. Its deepest value is in what it represents: a physical sample coming from another stellar system, possibly formed under conditions very different from our own. Every grain of dust, every molecule trapped in its interior, could tell a completely different story about how worlds are born and evolve beyond the Sun. So far, only 3 confirmed interstellar objects have been detected: Oumuamua in 2017, Borisov in 2019, and now 3I Atlas. Each showed distinct characteristics. Oumuamua displayed no tail or signs of cometary activity and left behind unexplained acceleration. Borisov behaved like a typical comet, with a bright coma and composition rich in cyanide and carbon, elements common in comets from our system. The hope with 3I Atlas is to obtain a third piece of this interstellar puzzle. If it can be observed again after its perihelion and shows signs of activity or spectral variations, it will be possible to analyze what compounds form it. If the presence of materials different from local comets is confirmed, we would have direct evidence that planetary chemistry in other systems can vary more than thought. Even if its composition is similar, that also has implications. It could mean that planetary formation processes follow more universal patterns. Another fundamental aspect is its internal structure. Some models suggest that interstellar objects, having been exposed to extreme vacuum and cold for millions of years, could have developed very compact outer layers, almost like a hardened crust protecting a more volatile core. This structure, if confirmed, would explain why some of these objects seem inactive until they are very close to the Sun. Unfortunately, access to this information depends greatly on spectroscopic observations. Without a probe nearby, everything must be inferred through the light it reflects or emits when interacting with solar energy. And that observation window is brief. Within weeks, 3I Atlas will pass from the solar glare to the dark background of outer space. That's why telescopes are already recalibrating their gaze towards the region where it must reappear. Because if Atlas shows us its true nature, even for a few days, it could offer us the most direct evidence we have ever had about how worlds form beyond the Sun. Although ground-based and space telescopes have improved notably, there are moments when even the most advanced technology is blinded. One of those moments occurs during solar conjunction. When an object passes behind the Sun as seen from Earth, that's precisely what is happening now with 3I Atlas. In astronomical terms, the object is in superior conjunction, aligned directly behind the Sun relative to our perspective. It is hidden by the solar glare. Trying to observe it with optical instruments would be like trying to see a firefly next to a lit spotlight in broad daylight. Even space telescopes like Hubble or James Webb, which operate outside Earth's atmosphere, are not designed to look directly near the sun. The intense solar emissions could damage their sensors. There are exceptions. Solar observatories like SOHO and STEREO use coronagraphs that artificially block the sun's light to study its atmosphere and coronal mass ejections. However, these instruments are not optimized for tracking small, faint objects like 3I Atlas, especially if its coma is not bright or its trajectory keeps it at the edge of the field of view. No images have been reported from active probes like Parker Solar Probe or Solar Orbiter, which could have a more favorable perspective. The main focus of these missions is to study the sun itself, and observation of passing bodies without a specific campaign is not always prioritized. Another factor that has limited the availability of images is recent instability in certain space agencies, with budget cuts or operational pauses that affected the publication of real-time data. For example, during part of the year, NASA faced technical and budgetary interruptions that halted the release of data from some minor missions. All this leaves the scientific community and the public in a frustrating position. We know that 3I Atlas is going through a critical phase, possibly the most revealing of its passage through the solar system, and yet we cannot observe it directly. In this visual void, astronomers focus on another type of data: orbital simulations and precise calculations that will tell when and where it will reappear, because that reunion with human sight will be decisive in checking whether the object remains intact or if something changed. While 3I Atlas remains hidden behind the sun, astronomers work with patience and precision to anticipate the moment it will be visible from Earth again. This wait isn't just a matter of calendar, but of celestial geometry, atmospheric conditions, and availability of adequate instruments. The object's reappearance will depend mainly on two factors: solar angle and angular separation between the Sun and 3I Atlas. For telescopes to observe it without risking sensors, the object needs to move at least 10 to 15 degrees away from the solar disk. This usually occurs a few weeks after perihelion, depending on its speed and orbital direction. According to current projections, it is estimated that by the end of November or the first days of December, the object should begin to move far enough from the solar glare to be detected again with optical telescopes. This period will mark the return of direct data and will allow verification of whether Atlas has undergone alteration during its close passage to the Sun. For that observation phase, coordinated campaigns between professional and amateur observatories are already being prepared. Medium-sized telescopes, equipped with special solar filters or fast-tracking systems, could be the first to capture its reappearance. Furthermore, high-sensitivity observatories like Pan-STARRS or the Very Large Telescope could provide key spectroscopic data. But there is also uncertainty. If the object has lost brightness, either due to fragmentation, loss of volatile materials, or simply due to its moving away from the Sun, it could become more difficult to detect. In that case, long exposures and particularly stable sky conditions will be required to achieve visual confirmation. Another important element will be the apparent motion of 3I Atlas in the sky. As it moves away from the Sun, its relative velocity will decrease, facilitating its tracking. However, if its trajectory has changed minimally, something possible if it has suffered non-gravitational pushes, its position could be deviated from original predictions. If so, real-time adjustments and tracking programs will be needed. Expectations are high. It's not just about confirming its presence, but about comparing previous data with new ones. A change in its brightness, apparent shape, color, or spectral behavior can offer crucial clues about its composition, structure, and evolution. For now, astronomy is in an active pause. And in that pause, what is at stake is not just observing an object. It's the opportunity to witness how the universe answers us after the silence. The visual return of 3I Atlas will not only be a moment of observation, but an opportunity to apply what the scientific community has learned from previous experiences. Although still scarce, the two previously identified interstellar objects, Oumuamua in 2017 and 2I Borisov in 2019, marked a before and after in how visitors from other stars are studied. Each showed radically different behaviors. Oumuamua, the first one, perplexed from the beginning. It showed no visible coma or typical signs of sublimation. Furthermore, it showed acceleration not explained by gravity alone, which triggered global debates about its nature. Hypotheses were proposed, from the expulsion of molecular hydrogen to more speculative theories related to extraterrestrial technology. Although none were confirmed, the object forced a review of models and consideration of new physical mechanisms to explain anomalous movements. Borisov, on the other hand, behaved much more familiarly. It exhibited a bright coma, gas and dust tails, and chemistry very similar to local comets. Still, there were notable differences. Its nucleus seemed more fragile, partially disintegrating much earlier than predicted. This detail made us think that, although its composition was similar to our comets, its thermal or structural history could be very different, possibly due to billions of years of exposure to interstellar cold. Now, with 3I Atlas, the focus is on what this new object can reveal to fill the gaps between those two extremes. Will it be another body with no surface activity like Oumuamua? Will it show active cometary behavior like Borisov? Or will it manifest something completely different? One advantage in this case is that 3I Atlas has been followed for a longer time before its perihelion, which has allowed for better estimates of its trajectory, brightness, and initial conditions. This baseline will facilitate the detection of any significant change once it reappears. If its trajectory has deviated, if its apparent shape has changed, or if it exhibits a different light pattern, this data can be directly compared with previous records. In essence, each new interstellar visitor functions as a unique piece in a cosmic puzzle. Comparing their behaviors, structures, and reactions to the solar environment helps build a more complete picture of what objects that form beyond our stellar neighborhood are like and how they vary. And with 3I Atlas about to emerge from the solar shadow, all eyes will be ready to see if this third piece fits or challenges everything that came before. As theories accumulate around 3I Atlas, it becomes crucial to establish a clear line between what science has confirmed and what remains, for now, informed speculation. In a phenomenon as uncommon as the passage of an interstellar object, it is natural for hypotheses to arise, but not all carry the same weight. What we do know, based on observations and orbital calculations, is that 3I Atlas has a hyperbolic trajectory, confirming its interstellar origin. Its speed, over 60 kilometers per second near the Sun, and its approach to perihelion in a zone very close to Mars's orbit are also well documented. Furthermore, estimates about its brightness and possible size come from standard methods of observational astronomy that compare absolute magnitude with its distance and solar angle. That data, while not exact, is within the typical confidence margin for faint, distant objects. Where speculation begins is in aspects like its exact composition, internal structure, or any unusual behavior it might manifest due to its close passage to the Sun. Some theories, for example, point to possible fragmentation if the object has a fragile composition or if solar energy has provoked internal tensions. However, there is no direct evidence that this has occurred so far. Discussions have also been generated about whether its passage could affect the solar environment or even have a correlation with recent solar activity. Although it is true that the Sun has shown an increase in active sunspots and coronal mass ejections, there is no empirical evidence that 3I Atlas has any influence on these processes, which respond to the star's own internal cycles. Another area where science crosses into speculation is the possibility that the object has an artificial or technological origin. This idea, which also emerged in the case of Oumuamua, has no observational support in the case of 3I Atlas. It is a line of thought that exists within the exercise of scientific imagination, not part of the academic consensus or serious publications on the topic. Clarifying these boundaries isn't a way to remove mystery from the object, but to give real value to the data that will be obtained in the coming weeks. What is seen when 3I Atlas reappears will be able to confirm, refute, or rethink much of what is being discussed today. But for those conclusions to have weight, they must start from a clear base. The scientific method remains the most reliable tool for deciphering the unknown. With 3i Atlas still hidden by the sun's light, the attention of the astronomical community is centered on the precise moment the object will reappear. For that stage, tracking from Earth will be fundamental and will not be limited solely to large space agencies or high-tech observatories. In fact, an important part of the first detections could come from the coordinated work between professional observatories and amateur astronomers. In the last 2 decades, amateur astronomy has undergone a notable transformation. With access to automatic tracking telescopes, high-sensitivity CCD cameras, and orbital analysis software, many enthusiasts around the world actively participate in observation campaigns for asteroids, comets, and transient objects. These collective efforts allow for broader and more constant coverage of the night sky. In the case of 3i Atlas, the reappearance will be particularly favorable for observers situated at mid-latitudes in the northern hemisphere. Once the object moves far enough from the sun in the sky, it will enter a strip where it can be observed just before dawn, in dark and clear skies. This initial period will be crucial for confirming its exact position and comparing the observed trajectory with the predicted one. Large observatories, like Subaru in Hawaii, VLT in Chile, or the Gemini telescope, will undoubtedly take prominence once the object's location is confirmed. However, the first sighting could come from a much more modest camera, operated from a backyard or local observatory. It has happened before. Unknown comets have been discovered or confirmed by amateurs before large institutions. What follows will be an intense phase of data collection. Efforts will be made to measure the object's apparent brightness, detect if it presents any coma or residual activity, and obtain spectra that allow analysis of its composition. Each image will contribute a new piece to the puzzle, and data will be quickly shared through international networks like the Minor Planet Center or the Central Bureau for Astronomical Telegrams. This global collaboration shows that in the current era, science is not exclusive to closed laboratories. It is open, distributed, and increasingly connected. With an object as exceptional as 3i Atlas, every pair of eyes counts. Every telescope, large or small, can provide vital information because once the object crosses back to the visible side of the sky, the race to understand it in real time will have begun. The observation of interstellar objects like 3i Atlas represents a technical challenge that goes beyond astronomical routine. These are not bodies that repeat known cycles nor can be predicted years in advance. Their passage is unique, brief, and unrepeatable. Therefore, the instruments used to study them must operate at the limit of their capabilities, adapting to unplanned situations and changing conditions. One of the main challenges is the low return signal. Being small, dark, and fast-moving objects, the light they reflect is minimal. Optical telescopes need prolonged exposures and high-precision tracking to not lose the object completely. This is where the use of robotic mounts, ultra-sensitive cameras, and predictive tracking software that allows anticipating the object's exact movement every second of exposure comes into play. In parallel, high-resolution spectrographs are key tools for extracting chemical information from the object's light. Even with a faint coma, it is possible to detect specific signals from molecules like water, carbon monoxide, or volatile organic compounds. This data, although fragile, can offer the first concrete evidence about 3i Atlas's formation environment. No less important are planetary radar systems, like the one operating from the Goldstone Observatory in California. Although this type of radar has been used more with near-Earth asteroids, there is potential to obtain weak reflections from more distant objects. In the case of 3i Atlas, a successful radar echo would allow more precise estimation of its real size, shape, and possible rotation, data from active solar missions, like Solar Orbiter or Parker Solar Probe, are also being evaluated. Although their main objective is the study of the Sun, these probes could capture emissions from the environment near 3i Atlas if they align correctly. Some cameras on these missions are designed to detect energetic particles and magnetic fields, which opens the possibility of indirectly measuring how the object interacts with the solar wind. This type of multidisciplinary approach has become more common in the modern era of space exploration. We no longer depend solely on one type of observation. Optical, spectral, magnetic, and plasma data are cross-referenced, seeking consistent patterns that reveal what eyes alone cannot see. All this demonstrates that to understand something truly new, science needs more than good instruments. It needs flexibility, coordination, and the willingness to look where it has never looked before. While the scientific community prepares to observe 3I Atlas again, one question continues to generate debate. What real consequences can the overload of solar radiation have on an interstellar object like this? The passage so close to the Sun isn't just a matter of trajectory. It's direct exposure to one of the most extreme environments in the solar system. During its perihelion, 3I Atlas has received an amount of solar radiation that multiplies by millions the energy it experienced during its transit through interstellar space. That energy is not homogeneous nor passive. It is composed of electromagnetic radiation of different types, charged particles, and fluctuating magnetic fields. Each of these elements has the potential to physically and chemically alter the object's structure. One of the most expected effects is the uneven heating of its surface, especially if it is a body composed of mixed materials like ices, porous rocks, or organic compounds. This heating can generate sublimation, internal cracks, or the sudden release of trapped gases, which together can provoke partial fragmentation or even complete rupture of the object. This phenomenon would not be new. Comets that have passed near the Sun, like Ison in 2013, have been completely disintegrated by thermal and gravitational intensity. But unlike them, whose structure was well known and monitored long before, 3I Atlas remains an enigma in almost all aspects relevant to predicting its resistance. Another possible scenario is that the object survived intact, but suffered subtle alterations on its surface, like the loss of outer layers, exposure of virgin material, or even the formation of a temporary thin atmosphere, difficult to detect but significant from a scientific viewpoint. This could be noticed in changes in its brightness, color, or spectral signature upon reappearing. Beyond thermal damage, the electromagnetic impact is also important to consider. If the object contains conductive materials, the passage through regions of high solar activity could have induced internal electrical currents, altering its magnetic field, its rotation, or even generating phenomena not yet well understood in interstellar bodies. All this is for now in the realm of possibility, but the truth is that no previously detected object has passed so close to the Sun under such active conditions as the current solar cycle. And if 3I Atlas reacts unexpectedly, those effects will offer us valuable clues not only about its nature, but about what something that has traveled for millions of years from another star can withstand. One of the most intriguing aspects of any interstellar object is its origin. Knowing where 3I Atlas comes from not only fuels scientific curiosity, but also helps understand how planetary systems form, evolve, and disperse in other parts of the galaxy. However, determining that origin is not a simple task. When an object like this enters the solar system, astronomers trace its trajectory from repeated observations. With that data, an inverse orbit is calculated, a simulation backwards in time to estimate from which exact direction in the sky it came. In the case of 3I Atlas, initial analyses suggest it entered from a region near the constellation of Sagittarius, a dense area in stars located towards the galactic center. But even with that information, it is not possible to point to a specific star as its point of origin. Interstellar distances are enormous, and objects like 3I Atlas could have spent millions, even billions of years traveling alone. During that time, the object could have been deviated multiple times by gravitational interactions with other stars, molecular clouds, or even rogue planets. Furthermore, the movements of stars are not static. They all move in the galaxy, following their own trajectories. This makes trying to trace the exact origin of an object like throwing a bottle into the sea and trying to guess on which coast it was thrown centuries ago. Even so, astronomers have created three-dimensional databases of stellar motion using missions like Gaia, which allows comparing the estimated trajectory of 3I Atlas with past positions of millions of nearby stars. So far, no stellar system has been identified as the probable point of expulsion of this object. The most reasonable thing is to think that it was expelled during the early stages of a planetary system's formation, a common event when giant planets gravitationally alter debris from the protoplanetary disk. Some of that debris managed to escape, initiating journeys that can last entire eras. This possible origin grants 3I Atlas immense scientific value. Its simple presence in our solar neighborhood represents a physical sample from another stellar system, one that has not been processed nor recycled by local planetary formation processes. It is, in essence, an ancient messenger from a place that has probably changed forever. And although we cannot know for sure where it comes from, we can learn something more concrete. How many more like it could be silently crossing between the stars? The discovery of 3I Atlas, like that of Oumuamua and Borisov, raises an inevitable question. If we have already detected 3 interstellar objects in less than a decade, is it possible that there are many more crossing our solar system unseen? The answer, with growing consensus among astronomers, is yes. The probability that these 3 findings are exceptions is low. It is more reasonable to assume that these objects are part of a flow of interstellar debris traversing the space between stars. The reason why, until recently, they weren't detected frequently has more to do with our technological limitations than with their scarcity. Before the rise of automated tracking systems like Atlas, Pan-STARRS, or the Catalina Sky Survey, telescopes had limited fields of view and detection of small, fast objects with unusual trajectories was extremely difficult. Many of these bodies simply crossed the sky unnoticed, lost in visual noise or discarded as measurement errors. With improvements in detection algorithms, more sensitive cameras, and greater sky coverage, the capacity to identify these visitors has increased significantly. Still, astronomers estimate that for every detected interstellar object, hundreds could have passed unregistered, especially if they were smaller or had trajectories less favorable for observation from Earth. Furthermore, not all objects that pass near the solar system penetrate it. Some could be deviated by the heliopause, the boundary where the solar wind loses strength against the interstellar medium, or pass through regions far from planets without leaving a perceptible trace. The study of these bodies has also led to considering the possibility that some are already trapped by solar gravity, orbiting in eccentric or almost undetectable trajectories. Models have been proposed that predict the existence of interstellar objects captured millions of years ago, camouflaged among asteroids and comets of solar origin. Because of all this, missions like the future Vera Rubin Observatory in Chile will be fundamental. This telescope, designed to scan the entire night sky every few nights, promises to multiply the number of detections of transient objects, including possible interstellar visitors. The question is no longer if there are more, it's how many are out there, crossing our orbits unseen, carrying secrets of stellar systems that perhaps no longer exist. And with each new detection, we get a little closer to understanding how connected and trafficked our region of the cosmos is. As the moment approaches when 3I Atlas reappears in the observable sky, the efforts of the scientific community are focused with surgical precision. It's not simply about seeing the object, but knowing exactly what to look for to make the most of the narrow observation window that will open after its passage through perihelion. One of the priorities will be to detect any change in its brightness. These variations can indicate cometary activity, mass loss, fragmentation, or alterations on its surface. Comparing the current light curve with the one recorded before solar conjunction will allow estimation of whether the object has suffered significant structural or physical changes. Another key measurement is a possible deviation of its orbit. If it is confirmed that its trajectory has changed, even minimally, that could indicate it has been affected by non-gravitational forces like radiation pressure or gas release. Current models have already predicted a theoretical route for its exit from the solar system. Any discrepancy will be a reason for detailed analysis. The spectra that can be obtained after its reappearance will be even more valuable. Through spectral analysis, scientists can identify chemical compounds present on the surface or in the coma, if there is one. The presence of volatile elements like water, carbon dioxide, or cyanide, for example, would suggest active cometary behavior. In contrast, a neutral or metal-rich spectral signature could imply a composition more similar to an asteroid. There is also interest in studying the object's rotation. If its light can be captured continuously over several nights, a rotation curve can be built that reveals its angular velocity and possible irregularities in its shape. This not only helps understand its physical stability, but can give clues about how it formed and whether it has suffered impacts or internal tensions during its interstellar travel. Finally, a less discussed but equally important aspect will be international collaboration in real time. The tracking of 3i Atlas will be shared among observatories on different continents, taking advantage of Earth's rotation to keep it under continuous observation. This coordination not only optimizes results but reflects how modern science moves today in networks, without borders and with common objectives. The countdown has begun. What is observed or not observed in the coming days will have a lasting impact, because in phenomena as rare as this, every piece of data collected can change what we understand about the universe we inhabit. Although 3i Atlas comes from outside our solar system, its close passage offers a unique opportunity to also study our own cosmic environment. Its trajectory, traversing the heliosphere, its interaction with the solar wind, and its response to the sun's intense radiation turn this object into a natural laboratory in motion, capable of revealing details that are normally difficult to measure directly. One of the most valuable aspects is how 3i Atlas reacts to crossing different regions of the inner solar system. Since it entered the solar environment, the object has passed through zones with varying levels of particle density, magnetic fields, and temperature. By observing its behavior at each stage, before, during, and after perihelion, scientists can study how these conditions vary throughout the solar system with greater precision. For example, if it is detected that the object begins to show cometary activity just upon reaching a certain distance from the Sun, that can indicate a thermal threshold from which certain compounds begin to sublimate. This is valuable not only for studying 3i Atlas, but also for refining models about comets from our own solar system. The effects of the solar wind can also be observed in real time. If during post-perihelion tracking the formation of an ion tail or changes in its direction are detected, it will be possible to estimate the strength and orientation of solar particle currents in that region. Even small variations could provide important data about the dynamics of the solar wind, especially in a stage of the solar cycle where activity is intense. The object on its path also crosses lines of the solar magnetic field. If changes in its brightness, direction, or behavior are generated at moments that coincide with magnetic reconnections or coronal mass ejections, the possibility opens up to study how a solid body responds to extreme solar events. Indirectly, 3i Atlas also helps test our own observation systems. The capacity to detect it, track it, and measure its behavior under such extreme conditions allows us to evaluate how prepared we are for future missions involving close transit to the Sun, both with probes and with other natural objects. In summary, although the object is a foreigner, its passage forces us to look inward again. It allows us to calibrate the solar scenario, better understand its invisible forces, and check to what extent we master or not the variables that govern the space we inhabit. Much of what we know about 3i Atlas comes from analyzing the light it reflects. This method, widely used in astronomy, allows estimating its apparent magnitude, its possible size, and some clues about its surface. But there is an important limit. Reflected light only tells part of the story. An object's magnitude is not always directly related to its mass or structure. A small but highly reflective body can seem larger than it is, while an object with a dark and rough surface can go unnoticed even if it has considerable dimensions. This phenomenon, known as the albedo effect, complicates any attempt to calculate the real scale with only optical observations. Furthermore, reflected light does not reveal direct information about the object's internal composition. It is possible that 3I Atlas has a surface altered by millions of years of exposure to interstellar space, a hardened, carbonized, or eroded layer that does not reflect the true nature of its core. This superficial crust could be what we are seeing, while the rest of the body remains completely unknown. To overcome these limitations, scientists complement optical observation with other techniques, like spectroscopy, which analyzes how light decomposes when interacting with different materials. However, even this tool faces challenges if the object does not emit clear signals, like an active coma or tail releasing particles into space. Another option is observations in non-visible wavelengths, like infrared or ultraviolet. Telescopes operating in these ranges can detect thermal emissions or processes that don't manifest in visible light. In theory, if 3I Atlas absorbed heat during its close passage to the Sun, it could now be emitting thermal radiation detectable from specialized observatories. But those signals can also be weak or confusing if the object is small or its surface does not retain heat well. That's why interpreting what we see and what we don't requires prudence. Sometimes, the most important thing isn't in the present data, but in the absences that leave a trace. Lower than expected brightness, lack of activity when there should be, a light curve that doesn't fit known models. In the case of 3I Atlas, what its light hides from us could be as revealing as what it shows. And as the moment of its visual reopening approaches, scientists will be attentive not only to the obvious, but also to what remains inexplicably silent. One of the most underestimated aspects in the observation of interstellar objects is their rotational dynamics. The way 3I Atlas spins on its own axis can offer key information about its shape, internal structure, and stability. This is not a minor detail. In fact, in small bodies, rotation can be a factor that determines whether the object remains intact or fragments. Most small-sized objects in space have irregular rotations. Some spin stably, like a balanced top, while others present chaotic rotations with multiple axes of spin, a result of past collisions or uneven internal forces. Detecting what type of rotation 3I Atlas has would allow inferring, for example, whether its mass is distributed uniformly or if it is composed of fragments weakly joined together, like a rubble pile structure. This type of analysis is done mainly through light curves. As the object rotates, it reflects sunlight differently according to its orientation. If it is elongated, for example, it will shine brighter when its broader side is oriented towards us, and less when it shows its narrower profile. This periodic variation generates a pattern that can be measured with precision and, when compared with models, allows reconstructing an approximate idea of its shape. In the case of 3I Atlas, any change in its light curve after perihelion could indicate physical alterations caused by the close passage to the Sun. Faster rotation, loss of symmetry, or chaotic variations would be clear signals that the object has experienced significant thermal or dynamic stress. Another point to consider is whether solar radiation has induced the Yorp effect, a subtle but real force that can accelerate or decelerate the rotation of small bodies due to asymmetric heat emission. Although this effect is usually more evident over long time scales, an object of reduced dimensions under intense thermal overload could experience detectable rotational changes in just a few weeks. There is even the possibility that, if its rotation has accelerated enough, 3I Atlas is near its structural limit, the point where centrifugal force surpasses the object's cohesion. If so, any small perturbation could provoke a fracture. Therefore, beyond its direction or speed, the way 3I Atlas spins could be key to understanding not only how it got here, but also how much longer it can endure on its path into the unknown. One possibility that cannot be dismissed is that 3I Atlas has suffered, or is about to suffer, partial or total fragmentation. This phenomenon is not rare among comets or small bodies of the solar system that approach the Sun too closely, but when we talk about an interstellar object, the scientific implications of rupture go far beyond the visual spectacle. If 3I Atlas fragments, the first thing that will change is its light curve. A sudden decrease in brightness, followed by the multiple appearance of faint light sources, would be one of the clearest signs that the object has divided into parts. Depending on the size and number of fragments, some could disintegrate quickly, while others could survive and follow their own trajectories, although similar to the original bodies. This scenario would not only reveal key aspects of its internal structure, like its cohesion, density, or type of bond between its materials, but would also open the possibility of studying how interstellar matter behaves when exposed to extreme conditions. Each fragment would offer a distinct point of analysis, both in brightness and in thermal or spectral behavior. There are already precedents in which comets have shown this behavior. Comet 73P Schwarzmann-Bachmann, for example, fragmented into dozens of visible pieces during its close passage to the Sun in 2006. But those bodies were part of the solar system, well known and monitored. In contrast, if an interstellar object like 3I Atlas fragments, we would be facing a unique opportunity to analyze virgin material coming from another stellar system, something never before achieved. Furthermore, rupture could alter the course of the fragments enough to complicate their tracking. Depending on their mass and the forces involved in the fracture, some pieces could deviate slightly, making their future localization difficult. That is why the observation window after perihelion will be critical. If fragmentation has already occurred or is in progress, every day lost implies the loss of unrepeatable data. It would also be evaluated whether the fragmentation was spontaneous, a product of internal tensions, or if it was induced by the combined effect of solar radiation, non-gravitational acceleration, and tidal forces near the Sun. Understanding this would allow improving models of the structural resistance of interstellar objects and better predicting their behavior in similar events. If the integrity of 3I Atlas has been broken, it will not mean the end of the study. On the contrary, it could be the moment when its interior is finally revealed, exposing secrets that its surface has kept hidden during millions of years of travel through the interstellar void. If something makes 3I Atlas an extraordinary object for science, beyond its trajectory or behavior, it is the possibility that its internal material has never been altered since its formation. Unlike bodies from the solar system that have suffered impacts, repeated heatings, and geological processes, an interstellar object could preserve in its core intact and primitive matter. This type of matter is known in the scientific community as virgin material. That is, particles or structures that have not been chemically or thermally modified since their origin. In the case of 3I Atlas, that origin could date back to the beginnings of a stellar system completely different from ours, perhaps even from a star that no longer exists, or from a planetary system that was destroyed or ejected, much of its debris into deep space. If the object has begun to show cometary activity, or if it has suffered some fragmentation, there exists the possibility that this internal material has been exposed. And in that case, every change in its spectrum, in its brightness, or in the way it interacts with sunlight becomes a direct clue about the chemistry of other planetary systems. Scientists will look for signs of compounds not commonly found in local comets. For example, atypical proportions of isotopes, complex organic molecules, or traces of exotic materials that could have been common in its native region. Even the absence of certain compounds would also be revealing. It could indicate very different formation conditions, like lower temperatures, different densities, or environments rich in radiation. The interest is not limited to chemistry. The texture of the fragments, their way of sublimating, or how they disintegrate can give information about their physical structure. If it is porous or compact, if it presents crystals, or if it is composed of amorphous grains. Each of these details adds a new piece to the puzzle about how solid bodies form and evolve outside the solar system. Without the need for a physical mission, remote observation of this exposed material already represents an exceptional scientific opportunity. But it also poses a paradox. The more active or damaged the object is, the more we can learn from it. Because in its partial destruction, 3I Atlas may be revealing what it has protected for millions of years of travel, a time capsule from another world, released just as it crosses ours. One of the most challenging aspects of studying 3I Atlas is its ephemeral nature. Unlike comets that orbit the Sun every certain decades, or asteroids that can be visited multiple times, interstellar objects enter the solar system only once and never return. That transient nature makes them scientific opportunities as valuable as they are difficult to take advantage of. Atlas, as its hyperbolic orbit indicates, is already on its way out. Every second that passes, it moves away not only from the Sun, but also from the reach of our instruments. Its speed is such that in a matter of weeks it will be practically undetectable. And when that happens, everything that hasn't been recorded until that moment will be lost forever. This fact imposes a different work logic than usual. There is no time for prolonged doubts nor postponed analyses. Decisions about what to observe, what instruments to use, and what data to prioritize must be taken rapidly, but without sacrificing precision. It is a race against time in which the observation window will not widen nor repeat. This same fleeting nature also imposes a particular emotional burden on the scientific community. Knowing that one is facing a unique and unrepeatable phenomenon generates a different tension, a balance between scientific rigor and the urgency to take advantage of every instant. Astronomy in this case stops being patient and contemplative, and becomes a discipline of quick reflexes and immediate collaboration. Furthermore, the fugacity of 3I Atlas is not only a limitation, it is also part of its charm. Its passage reminds us that the cosmos is in constant movement, and that not everything that occurs out there adapts to our calendars or capacities. Sometimes messages from the universe arrive in the form of a silent, vast and distant object that crosses in front of us and disappears before we can fully understand it. But it is precisely that brevity that gives it so much value. Every image obtained, every spectrum analyzed, every piece of data recorded automatically enters a special category: unrepeatable. Because when 3I Atlas disappears into the dark background of space, only our observations and questions we haven't yet formulated will remain. And among those questions one repeats in silence, how many more are crossing right now, invisible in their own borrowed time? Despite all attention seeming centered on 3I Atlas, its brief visit also tests another crucial aspect: our technological capacity to respond to the unknown. Every phase of its passage, detection, tracking, has been a kind of global exam for terrestrial and spatial observation systems. The detection of this type of object demands unprecedented coordination between institutions, countries, and telescope networks. Unlike a known comet that can be scheduled months or years in advance, an interstellar visitor requires almost immediate responses. From the moment its hyperbolic trajectory is identified, every minute counts. And on this point, recent technological advances have been determinant. Automated image analysis systems, like those used by the Pan-STARRS telescope, are capable of comparing thousands of objects per night, recognizing unusual patterns and trajectories that escape the common. This type of algorithmic intelligence has been key to detecting not only 3I Atlas, but also many other transient bodies that previously went unnoticed. The operational flexibility of large observatories has also been tested. Many of them, like the VLT or the Subaru and Keck telescopes, usually have agendas planned months in advance. However, when an event as rare as this appears, they must reprogram their observation almost in real time. That capacity for adaptation, both technical and administrative, is a clear signal of the global commitment to frontier science. Another factor has been citizen collaboration, driven by accessibility to quality astronomical instruments. Open data platforms have allowed amateur astronomers to contribute with valuable observations, generating a monitoring network much wider than any agency could sustain on its own. However, 3i Atlas has also exposed certain limitations. We still lack active missions designed to intercept or visit interstellar objects quickly. Space mission development times usually far exceed the duration of events like this. That's why the possibility of creating rapid response vehicles, stationed at strategic points in the solar system, ready to be launched when an unexpected visitor appears, is beginning to be discussed. At its core, 3i Atlas has also been a mirror. It doesn't just reflect the sun's light. It reflects what we are capable and still incapable of doing when the universe presents us with a fleeting but profoundly valuable mystery. When an object like 3i Atlas crosses the solar system, it doesn't just leave us data, it leaves us questions. It leaves cracks in what we believed we understood about the cosmos. Because no matter how sophisticated our technology is or how complete our models seem, an interstellar body like this breaks the comfort of certainties. Its unexpected appearance forces us to reconsider how prepared we are to detect and study phenomena that don't adjust to the patterns of the solar system. Until a few years ago, the majority of astronomers thought the probability of observing an interstellar object was very low. Today, with 3 identified in less than a decade, that assumption is no longer sustainable. This forces a revision of priorities. How many resources are we investing in the search for objects that come from out there? And how many tools are we designing specifically to study them, beyond adapting what already exists? The arrival of 3i Atlas evidences that it is not enough to wait for data to fit known models. We must be ready to build new frameworks when data doesn't fit. Furthermore, this type of event not only questions astronomy, it also opens doors in astrobiology, physics of extreme materials, orbital dynamics, and planetary formation. If at some point we manage to identify unique chemical compounds or unusual molecular structures in an object like this, how we think about the origin of planets and, by extension, of life in different regions of the galaxy could be redefined, but beyond the technical, 3i Atlas pushes us towards a broader cosmic awareness. It reminds us that we live in an open solar system, connected, exposed to visits from other stellar regions. Every body that enters and leaves is a story that was not written here, a narrative that briefly reaches us before continuing its course. That perspective, by itself, changes the way we understand our place in the universe. We are not in a closed bubble. We are on a galactic highway where fragments of other worlds pass, observe, or at least, allow themselves to be observed and continue their journey towards destinations we will never know. Faced with that scenario, perhaps the most valuable thing 3i Atlas leaves us is not an answer, but the urgent need to ask ourselves better questions. Once 3i Atlas disappears from our skies, the only thing that will remain is its legacy: scattered data, fragmented observations, records of light and shadow. But in science, that faint trace can be more powerful than any prolonged presence. Sometimes the deepest discoveries are born not from what remains, but from what barely lets itself be seen. The legacy of 3i Atlas will be, above all, a scientific precedent. Every refined model, every adjusted algorithm, every protocol tested during its passage will serve as a base for future detections. We don't just learn from the object itself, but from the way we studied it. In other words, its fleeting transit has acted as a real simulation, a kind of exercise in real time for what is to come. Furthermore, its data will become part of global astronomical catalogs, available for researchers who maybe years later discover correlations that are not evident today. Because in science, nothing is lost if it is well documented. And every pixel of an image, every spectral line, every calculation error, also forms part of the collective learning. The most probable is that part of 3i Atlas's legacy will also consist of new questions. Why didn't it show activity upon approaching the sun? Why was its brightness so erratic? Was it really a unique body or a fragmentation of something larger? Some of these questions might not have an immediate answer, but they will remain floating in scientific debate, waiting to be approached with better data or technologies not yet invented. There is also value in the symbolic. In a world increasingly saturated with information, an astronomical event that requires precise attention, patience, and international collaboration functions as a reminder of human potential when working together. With curiosity as the engine, Atlas was observed by telescopes on different continents, analyzed by open academic networks, and followed by enthusiasts who shared their data from balconies and mountains. That collaborative fabric beyond the technical is an essential part of the legacy. Because we are not only learning about bodies that cross the solar system, we are understanding how to respond collectively to the extraordinary, how to organize knowledge in real time, how to build science from moments that by their very nature cannot be repeated. And so, although 3i Atlas gets lost in the darkness of deep space, it will leave behind something more lasting, the trace of an instant that forced us to look upwards with new eyes. Throughout the history of astronomy, many important discoveries have arrived by surprise. But with the appearance of objects like 3i Atlas, that surprise is becoming something more frequent. What was once considered improbable, the visit of a body from another stellar system, begins to feel, if not common, at least possible within the framework of a new cosmic normality. This change of perspective is profound. For centuries, the skies were seen as a fixed, predictable stage, where everything followed regular trajectories. Planets, comets, stars, each with its place and its rhythm. But interstellar objects break with that vision. They are pieces that don't quite fit in the solar system, but cross it as if reminding us that there is no real frontier in interstellar space. 3i Atlas is not simply a curious case, it is part of an emerging pattern that suggests our cosmic neighborhood is more dynamic than we imagined. The spaces between stars are not empty. They are full of debris, particles, wandering bodies. Some of them cross planetary systems silently without leaving a trace. Others, like this one, let themselves be seen only for an instant. That new understanding obliges us to modify how we understand the concept of the solar system, no longer as an isolated environment, but as a stop within a much larger network, a galactic network through which fragments of foreign histories travel. Objects like 3i Atlas are physical witnesses of those narratives. They are not anomalies. They are part of the natural flow of matter on a galactic scale. This recognition also has implications for the search for life outside Earth. If solid bodies can travel from one system to another, why not also complex organic compounds? Why not, even on unimaginable scales, structures that carry information or conditions favorable for life? Although these ideas touch the limits of scientific speculation, they also open doors to explore possibilities that were previously dismissed as improbable. What was extraordinary yesterday may be routine tomorrow. In a universe in constant movement, the improbable is not rare, it is just difficult to see in time. And every object like 3i Atlas is a reminder that we are still taking the first steps in understanding how open, crossed, and interconnected the paths of the cosmos are. The passage of 3i Atlas through our solar system has been, above all, a constructive warning. Not a threat, but a reminder that we are not completely prepared to face nor take advantage of truly unexpected phenomena. Science, although based on observation and logic, often stumbles when the unknown gets ahead of foresight. This type of object forces us to work under conditions that break with conventional protocols. Short times, limited observation windows, non-repeatable trajectories. These are not missions planned for decades, but immediate responses to opportunities that will not return. And there is where an as-yet unresolved tension in modern science is revealed. The gap between what we know how to do and what we could do if we were better prepared. One of the lessons left by 3i Atlas is the need for rapid response scientific infrastructure, flexible telescopes, automated international coordination, the capacity to redirect satellites or probes in real time. Even the design of spacecraft on standby, ready to intercept unexpected objects, is returning to scientific conversation, no longer as science fiction, but as a realistic strategy in the face of a cosmos that doesn't give warning. But beyond technology, the greater challenge is cultural and structural. Can science adapt to chaos without losing its rigor? Can it act with agility without sacrificing veracity? Can it open itself to the uncertain without falling into empty speculation? The case of 3i Atlas demonstrates that yes, but with effort and not without difficulties. The interesting thing is that we are not alone in this process. The global scientific community has demonstrated that even in the face of unplanned events, it can activate efficient collaboration networks, share data in real time, and build useful models in weeks. It is a collective exercise of distributed intelligence that activates when the unknown knocks on the door. However, if we want to fully take advantage of the next 3i, whatever its name, we must assume a new posture, that of science ready for chance, for the singular, for phenomena that don't fit into statistics. Because in the end, the future of space exploration will not be decided only in laboratories or control rooms, but in our capacity to react to what we didn't expect to see. And 3i Atlas, by crossing our sky for an instant, has reminded us that the universe doesn't wait. It only offers an opportunity and then continues its course. As the story of 3i Atlas begins to fade in time, just as the object itself does in space, what remains is not just a set of data. What remains is a change in perspective. Because what this interstellar visitor has provoked goes beyond its physical passage through the solar system. It has opened a different window, a new way of thinking, of anticipating, of observing. For years, astronomy has been based on repetition, orbital cycles, periodic events, predictable systems. But interstellar objects break that pattern. They don't repeat, they don't orbit, they don't wait. And in that lack of predictability, there is a profound teaching. The universe is not organized for us to understand it. It is we who must adjust our tools, methods, and questions to be up to the task of its complexity. Atlas has made us see that in reality, the exceptional thing is not its existence, but our limited capacity to detect it before. Today, we can track these bodies because our technology and mentality have begun to adapt to the unpredictable. And that is perhaps the most transformative consequence of this whole process. We haven't just learned about the object, we have learned to look in another way. In that sense, 3i Atlas doesn't close a story, it opens many. It has stimulated new lines of investigation into primeval materials, galactic trajectories, exotic chemistry, and thermodynamics under extreme conditions. But it has also reinforced broader debates about how we prioritize scientific investments, how we democratize access to data, and how we balance rigor with urgency when time is short. And something else has changed: the relationship between science and society. Millions of people followed the trajectory of this foreign body. They marveled at its rarity, asked questions, shared images, theories, doubts. That phenomenon of collective interest turns 3i Atlas into something more than a scientific object. It becomes a shared story, a narrative that connects communities around the world with a fragment that comes from another corner of the galaxy. Thus, while 3i Atlas moves away towards darkness, it leaves a new light ignited in our way of looking, a light that doesn't only illuminate the object, but everything that will come. Because the sky is no longer just a place where we look for answers. It is increasingly a place where we learn to ask questions we didn't even know how to formulate before. One of the most subtle but profound effects of the passage of 3i Atlas has been to push us to reconsider what the origin of something really means. In astronomy, we usually talk about where an object came from in spatial terms, its trajectory, its stellar system, its initial direction. But this type of interstellar visitor poses another, more complex perspective. What if origin is not just a place, but also a moment, a history of expulsion, of transit, of transformation? 3i Atlas is not simply a body that crossed the solar system, it is a consequence of an ancestral event. Perhaps it was expelled by gravitational interaction in its system of origin, or by the chaotic formation of a giant planet. Maybe it was pushed by a nearby star or even by a supernova. Whatever the case, its origin no longer exists as a stable coordinate. It is a sequence of movements, not a fixed point. That idea resonates with another key notion in current science: the concept of dynamic trajectory. Objects don't just have a position, they have a history. And that history, although we can't always reconstruct it completely, leaves traces in its rotation, in its composition, in its way of reacting to the environment. That's why understanding a body like 3I Atlas is not just projecting it into the future, it is also tracking clues it left on its journey. This leads to a change in mentality. It is no longer enough to know where it came from in terms of the visible sky. We must ask ourselves what events made it what it is. Was it altered by collisions? By intense magnetic fields? By extreme radiative environments? Those questions don't have easy answers, but they mark a transition in how we approach the science of cosmic movement. Not as a flat map, but as an evolutionary narrative, and in a certain sense, that same logic could be applied to how we observe our own solar system. If objects like 3I Atlas can leave, is it possible that fragments of our environment have left towards other systems? Perhaps right now a piece of our sun's history is crossing some distant system, awakening there the same questions we ask ourselves today. In a universe where everything moves, perhaps there are no fixed origins, only narratives of displacement. And 3I Atlas is not just a visitor, it's a page torn from another book, flying through space, briefly landing in our history to remind us that no horizon is definitive. When it was announced that 3I Atlas was receiving an unprecedented solar overload, many imagined a collision of forces, a traveling object forged in another corner of the galaxy facing up close the star that governs our system. But beyond the visual drama, what really occurred was something much more powerful: an encounter between worlds separated by time, space, and origin, united by a brief but profound interaction. During its close passage to the Sun, 3I Atlas was bombarded by an intensity of radiation, heat, and solar particles that no observed interstellar object had experienced with such closeness. This solar overload was not just a physical phenomenon, but a natural experiment. The Sun, with all its violence and vitality, became a real frontier between what comes from outside and what belongs to the solar system. This encounter allowed us to see for the first time how an interstellar body responds to an energy source like ours. Does it fragment? Does it activate? Does it resist? Does it change course? Each of those answers traces a sharper line between what we know and what we still don't understand about the cosmos. But it also redefines a deeper question: where does the solar system really end, and where does the rest of the galaxy begin? 3I Atlas, by crossing that solar line, brought with it more than particles or spectra. It brought context. It reminded us that the solar system is not a closed system, that it is open to debris, histories, and fragments from other places, that interstellar space is not empty, but full of memory and movement, and that the Sun is not just the center of our neighborhood, but a point of contact with everything that is beyond. The most remarkable thing is that this event didn't end the moment the object disappeared from the visual field. On the contrary, that's when it truly began. Analyses, simulations, debates began. The process of integrating this visit into our accumulated knowledge began, of turning the exceptional into part of the map. And if this story leaves us with anything, it is an uncomfortable but revealing certainty. The interstellar is no longer an abstract theory. It is real, present, and active. And its passage not only challenges our instruments, but our ideas about belonging, limits, and origin. Atlas is leaving, but it left us more open than ever to the universe that surrounds us.